Welcome to lecture number 5 of my series on vector calculus. In this series, we have been taking a look at the holy trinity, so to speak, of vector calculus: gradient, divergence, and curl. And so far, we have introduced all three of them. In the last lecture, we met the curl of a vector field A as another vector field, curl of A, which was defined basically as circulation per unit area. To be more precise, the definition of curl of A at a point P was as follows. It is a vector whose projection in the direction of a vector n hat is given by a limit. The limit of the circulation of this vector field A in a boundary of a flat region sigma, that is this boundary gamma of a flat region sigma, divided by the area enclosed by sigma, where this region sigma is a two-dimensional flat region normal to n hat, and of course the limit that we have to take is a limit in which this area shrinks down to 0 while still containing the point P in it. We had also seen that, at least in Cartesian coordinates, you can express this curl of A in terms of the nabla operator crossed with A. That is, it's a vector field whose components are given respectively by del y of Az minus del Ay del Z, del z of Ax minus del Az del X, del X of Ay minus del y of Ax. This last statement, of course, here is wrong. So, it should be del Ax del y. Now, with our earlier member of the holy trinity, the divergence, we had seen a particular result. The divergence was defined essentially as a limit in a similar fashion, in this case a limit of flux per unit volume, and what we did was we turned this definition on its head and expressed the flux through a closed surface in terms of the volume integral of the divergence of the same vector field over the region bounded by this closed surface. This essentially was Gauss divergence theorem. The question is, can we do something very similar with the curl? After all, the curl is, in a sense, like the divergence. The divergence was flux per unit volume, in a limiting fashion, of course. Similarly, the curl essentially is related to the density of circulation, in this case, surface density of circulation. So it stands to reason that something similar can be done with the curl, and we should be able to write down the circulation over a closed loop in terms of an integral of curl of the same vector field over maybe the surface bounded by that loop. Indeed, it turns out to be true, and this is a very celebrated theorem in mathematics called Stokes' theorem. As we had mentioned in an earlier lecture, the Gauss divergence theorem that we had seen there and this Stokes' theorem actually are two sides of the same coin as far as advanced mathematics is concerned. But at our level, these two theorems have been proven separately. And that is what we are going to do now. We have already proven Gauss divergence theorem in an earlier lecture. What we are going to do now is prove Stokes' theorem. Now, given the fact that curl of A's projection in the direction of n hat happens to be the limiting value of the circulation of A about a planar loop divided by the area of the loop, makes it obvious that if curl of A is a constant vector field, then for a planar loop gamma, we can always write the circulation of the vector field A about the loop gamma as simply curl of A dotted with the area vector. Here S vector is basically the area vector denoting the flat surface bounded by the loop gamma. Now, the question of course is, What if the loop is not planar and or curl of A is not uniform? In each of these cases, we cannot use the simple formula that curl of A dotted with S is going to give you the circulation. However, what we can fall back upon here is exactly the same thing that we have used over and over again wherever we had a simple formula which we cannot use because of something varying. That is, break up our region into tiny pieces. So what we can do is we can take a surface which bounds our loop gamma. Any surface will do actually, as we will see soon, as long as it's bounded by gamma, and break it up into many tiny pieces. Each piece has to be so small that it is nearly planar. Now, if your original curve was not a planar one, then it is impossible for you to find the surface bounded by it, which is planar. Indeed, even if the original curve was planar, apart from the one flat surface which is bounded by it, there would be many more surfaces which are bounded by the same curve but which are not planar. However, what we are saying is, if you take such a surface and break it up into many tiny bits, the tiny bit of even a curved surface always looks like a flat bit. And therefore, each piece can be made so small that it is nearly planar, and over that particular small bit, curl of A can hardly vary, so that it has a nearly uniform curl of A. So for that small bit, of course, the circulation of A along the boundary will be given, at least approximately, by the dot product of curl of A. In that bit, there is curl of A I, where I stands for the ith bit, dotted with delta Si, where delta Si is the normal to this ith bit. Note that because the ith bit is nearly planar, you can define a unique normal vector to it, and therefore can talk of a vector area delta Si for that particular piece. Now, when you add all of these circulations up, a very important thing will be that there will be many regions where the lines will double up. That is, if you have an original curve like this, and you have broken it up into many pieces like this, you would have pieces which are actually there in multiple curves, at least shared by two curves. But it is very easy to see that the contributions to the circulation of all of these would cancel. We had argued why this would be in detail in the last lecture, and I'm pretty sure I don't really need to repeat that argument here. So what you end up with ultimately is, when you add all of these circulations, is actually the circulation about just the outer boundary. Remember once again, the outer boundary, that is the boundary gamma, has no other pieces coming from other sides to cancel their contributions. So when you add all of these curl of A on the ith piece dotted with delta Si, sum them up over all I, what you're going to land up with is at least approximately the circulation over the entire contour gamma. Note that this is approximate not because of the cancellation of internal lines being approximate. That is exact. This is approximate because as long as your regions are large, so that they are not really flat or don't really have uniform curl of A inside, replacing the circulation in the boundary of a small region by curl of AI dot delta Si, that is where the approximation lies. Now, when does this become exact? Obviously in the exact where these variations can no longer occur. That is where the largest of the areas that you are breaking up your surface into, that shrinks down to 0. So, the circulation of the vector field A over a closed loop gamma, which is the boundary of some region sigma, is given by this limit. You break up your surface sigma into many tiny pieces. Each piece has its own area vector delta Si, You dot the curl of A at this piece, curl of A I with that, sum over all I, and then take the limit as the largest of these pieces shrink down to 0. And this is exactly what we define as a surface integral of curl of A. So this leads us directly to Stokes' theorem. The line integral A dot dl over a closed loop gamma, which is the boundary of a surface sigma, is given by the surface integral of curl of A dot ds over the surface sigma. Written in a more compact notation, circulation of A over gamma equals del sigma is the flux phi of curl of A over the surface sigma. So this relates circulation of a vector field on the one hand with a flux through a surface bounded by the loop over which the circulation is being taken on the other. Now contrast this with Gauss' theorem, which says that the surface integral of a vector field A over a surface sigma, which is the boundary of a region tau, is equal to the volume integral of divergence of A over the volume tau. The similarity between these two laws should be noticeable, and as I have said before, the similarity is not an accident. In advanced mathematics, both of these two theorems, Stokes and Gauss, are actually two sides of the same coin, two special cases of a more general theorem, which is best expressed in the language of differential forms. Since this language is not accessible to us, we will have to be satisfied with these two theorems stated as two separate but very, very similar theorems. Before we go on any further, let me stress two small but very, very important points about the structure of Stokes' theorem. The first of these involves a convention. Note that in Stokes' theorem we are actually connecting two things, a circulation about a loop and a surface integral of a related vector field. Now in both of these calculations, there is a sign convention involved. As far as circulation is concerned, a very important question is that of the direction in which the loop is being traversed. At the same time, when you are calculating the surface integral over this surface, which because it has a boundary gamma is an open surface, the choice of the normal is not predefined. An open surface has two normals and you could have used either of the two choices. The point I am trying to make here is the choices of the direction of traversal of the loop gamma and of the normal that is to be used when you write down ds vector. These are not two independent choices. It's easy to see that they could not be independent. After all, if they were, I could be able to change the direction of traversal of my loop gamma without changing ds vector, in which case the left hand side of the Stokes theorem would have changed sign while the right hand side would not have. And so, if the Stokes theorem had been correct in our first convention, it would definitely have failed in the second, unless by some special circumstance the circulation happened to be 0. In which case, of course, changing its sign doesn't really matter. In general, the circulation of a vector field in a closed path is not 0. So this sign change would make a difference. And it's easy to see that you cannot possibly choose ds vector independent of the direction of traversal. These two notions of the direction of traversal of a loop and the choice of the normal for the surface integral are connected by what is called the right hand rule. You imagine that you are curling the fingers of your right hand in the direction in which the loop is being traversed. Of course, you have to imagine a better drawn figure than mine, but still. Then the thumb of your right hand, extended thumb, will give you the sense in which the direction of S has to be chosen. Of course, this only gives you a sense, and basically the idea is DSS in neighboring regions has to be chosen using continuity. That is, if the DS here is pointing like this, which as the right hand rule tells you, the ds next to it cannot point like this. It has to be pointing like this, which is essentially what you can determine by just using the right hand rule. On the other hand, if the direction of traversal was like this, that is, if your fingers of your right hand rule curled along the direction of traversal went like this, then your thumb cannot point this way. Then your thumb would have to end up pointing this way. At least if you are using a right hand. Which is why then the choice of your ds would have to be like this. That is, of course, on this segment it will have to be like this, on this segment it will have to be like this, and so on. Notice that in this case, if you were to reverse your sense of traversal, your line integral, the circulation would change sign, but because you are forced to change your ds along with it, the surface integral on the right hand side of Stokes' theorem would also change sign, which means that no ambiguity about one side changing sign and the other not will occur. So this was my first point. The second point is actually a bit more non-trivial. It involves the choice of the surface sigma, whose boundary gamma is going to be. A moment's thought would tell you that there are actually infinitely many choices possible for a surface if only its boundary is given. Indeed, if the loop given was a planar one, you would be tempted perhaps to use a flat surface, but that is by no means the only surface which has that loop gamma as the boundary. And if a loop is not a planar one, then you don't even have a unique flat surface to fall back upon. In this picture, I have drawn two surfaces, sigma 1 and sigma 2, both of which actually have gamma as the common boundary. So the question is, when I calculate the circulation A dot dl and try to relate that to the surface integral of curl of A with dot ds, which of the two surfaces should I use, sigma 1 or sigma 2? What does Stokes' theorem say? Is circulation A dot dl equal to curl of A dot ds over sigma 1 or curl of A dot ds over sigma 2? And the answer is, it does not matter which surface you choose. In other words, as long as gamma is the boundary of the surface, no matter which surface you choose, curl of A dot ds will have the same integral over the surface. So it will not matter whether you choose sigma 1, sigma 2 or any of the infinitely many other surfaces whose boundary is given by gamma. To realize why that is, just take a look at the union of sigma 1 and sigma 2. Sigma 1 union sigma 2 is a closed surface. And so if you were to integrate curl of A dot ds over this closed surface, sigma 1 union sigma 2, then of course what you can use is the fact that this is the boundary of a region, the region tau, which is bounded by this overall closed surface. And Gauss' theorem tells us that this surface integral over a closed surface can then be related to the volume integral of the divergence of the vector field here. That is, divergence of curl of A integrated over the volume tau. But we know that divergence of curl of a smooth vector field A is 0. So this surface integral vanishes. So surface integral over the combined surface sigma 1 and sigma 2 is 0 for the curl of any A as long as A is smooth. So that means that the surface integrals over sigma 1 and the surface integrals over sigma 2 cancel each other out. However, note that when we are doing a surface integral over a closed surface, we are bound to use the outward normal. The normal drawn in blue and orange in your picture right now. But when we are using Stokes' theorem, our normal choice is bound by the right hand rule. For example, if we were to traverse the loop gamma in this particular direction, then the right hand rule would tell you that this is the normal you have to use for this surface, and for this surface as well, you have to use this normal. So in this case, the surface integral over sigma 1 is the one which we had obtained before, But the surface integral that we have to use for Stokes' theorem is actually the negative of the surface integral over sigma 2, which cancelled that over sigma 1. So as long as we choose the normal using the right hand rule, sigma 1 and sigma 2 will give you the same surface integral. And this is true not only about sigma 1 and sigma 2 in particular, this is true about any two surfaces which share gamma as the boundary. Because with any two of these surfaces taken together, you can get a closed surface and repeat this whole argument. Now that we have both Stokes and Gauss theorem under our belt, let us try to use them to prove two theorems that we had already met before. In fact, we had already proven these two theorems before. These are theorems which involve using the nabla operator twice on a field. The first of these theorems was the one which involved applying the curl operation on gradient of phi. And the second one involved taking the divergence of curl of a vector field A. If the scalar field phi in the first case and the vector field A in the second happen to be smooth fields, that is, happens to have at least second partial derivatives which are continuous, then it turns out that curl of grad phi and divergence of curl of A are both 0. We had established this before using standard properties from calculus. Let me give you this cute proof that we are promising here using Stokes' theorem and Gauss theorem together. First, let us take a look at the identity involving curl of grad of phi. Let's integrate curl of grad of phi dot ds over a surface sigma, any arbitrary surface whatsoever. Since this is the curl of a vector field, namely gradient of phi, using Stokes' theorem we can relate this to the line integral of the gradient of phi, this vector field, dot dl over gamma, where gamma is the boundary of sigma. And of course, being the boundary of a surface, this has to be a closed line. Now, grad phi dot dl, by the definition of gradient of phi, is simply d phi, the change in phi, or the infinitesimal change in phi. And when you go all the way along a loop, closed loop gamma, the net change in phi over this closed loop has to be 0 because phi has to return to its original value when you're back to the original point. So over any arbitrary surface whatsoever, the integral of curl of grad phi has to vanish. And since this surface is completely arbitrary, the integrand here must be 0, that is curl of grad phi must be 0. Let us now go on to the second of these identities, the one involving divergence of curl of A. And here it should be pretty clear what we should do. Because we are involving a divergence here, we are going to try doing a volume integral over an arbitrary volume. Divergence of curl of A integrated over any volume tau. Gauss theorem will tell us that this has to be the integral over the boundary sigma of this region tau of curl of A dot ds. So this is just Gauss theorem being applied here. Now since we are talking of a surface integral of curl of a vector field here, we can use Stokes' theorem on this and replace that by the line integral of A dot dl over gamma, where gamma is the boundary of this sigma, which of course is in turn the boundary of tau. But the boundary of a boundary is always 0. Or in other words, since sigma is the boundary of a region, it has to be a closed surface and as such can have no boundary. Therefore, the line integral is being done over a line of 0 length, so to speak, and therefore it must be 0. And since divergence of curl of A gives you a 0 integral over any arbitrary volume whatsoever, the integrand in this case, divergence of curl of A, must be 0 itself. So these rather cute little proofs give you an inkling of the way in which we can use the two theorems, Gauss and Stokes, to derive many important results. These are actually results which we had already seen before, And frankly, the proofs here, though cute, may not be very important. But these theorems can be used in many, many more ways. And in the long run, you will definitely come to appreciate that these are two of the most important theorems that you must have in the toolkit of a theoretical physicist. Now the proof of Stokes' theorem that we have given in the lecture so far, the one that I am calling proof number 1, essentially uses the definition of curl of A as something which has to do with the surface density of circulation. Just as in the case of the divergence theorem, where there was a more formal proof given more mathematically, a similar proof can also be given for Stokes' theorem. This proof essentially hinges on the fact that curl of A has an expression which in Cartesian coordinates at least looks like del cross A, and then it goes on to use standard calculus via some results which may not be familiar to you right now. Results like Green's theorem in a plane and so on. We are going to talk about this second proof in our next lecture. For the rest of this lecture, let us explore this question. Curl of A is del cross A. That's something we had already shown in the last lecture. But this proof or this particular formula is valid only in the Cartesian coordinate system. What about other coordinate systems? But before we go on to talk about other coordinate systems, let us revisit our proof that curl of A is del cross A, and let's try to do the math slightly better this time. Let me just remind you what we had done in the last lecture. In order to figure out the curl of A, at least the z component of curl of A, we had taken a loop in the xy plane. Calculated the circulation in the loop divided by the area to find the surface density of circulation, and then taken the limit in which this loop shrinks down to a point. Since, at least for the z component, all this is happening in the xy plane or in a plane parallel to the xy plane where z is a constant, I'm going to suppress the z coordinate just for the sake of simplicity in the discussion that follows. So what we did was to take a loop A, B, C, D, A with coordinates for A, B, C and D as shown in this figure and calculated the circulation in this loop. Of course, that was the circulation A dot dl over this loop gamma, which was a sum of 4 terms. The contribution from AB, since AB is in the I direction, I hat direction, that is in the x direction, A dot dl there just became AX dx. A dot dl here became AY dy. For the same reason, dl essentially is in the y direction. Here you have AX dx again, but with x decreasing over CD, and AY dy again with y decreasing for dA. Now I don't really want to repeat the whole argument that we had given in the last lecture, but I will have to revisit a bit of that to address a question which the more mathematically minded among you might have. So in order to do this, let's focus on a pair of sides of this particular loop. Let's say AB and CD, these two parallel sides. The contribution to the circulation from these two sides is simply AX delta x at y held at y minus delta y, that is for the side AB. And AX delta x is a minus sign. Remember, it's a decreasing x that you have here, with y held at y plus delta y by 2. And this, when you compare the two values, gave rise to this term minus del y of ax times delta y. That came from the change in ax when y changed from y minus delta y by 2 to y plus delta y by 2. times delta x, which came in for a ride, plus higher order terms. You did something similar for the other two legs of this loop, and you ended up with the other term that was plus del del x of ay into delta y delta x, again plus higher order terms, and then you just divided the whole thing by delta x delta y, took the limit as delta x and delta y went to 0, and you landed up with the z component of the curl. Now the more mathematically minded among you might be inclined to ask that this particular step, this integral being replaced by ax delta x, is that at all a legitimate thing to do? You might say, why not? After all, I did justify this the last time by saying this side is small, that is delta x is a small value, so ax hardly gets a chance to change. So that's why we are replacing the integral ax dx over ab by ax, the value there, times delta x. However, the question would be the following. Note that here on this particular line, x changes from x minus delta x by 2 to x plus delta x by 2. Of course, over a very small range of delta x. So, it might seem legitimate to suppress the variation of ax here. However, note that the contribution that we have to the curl in the end is really coming from the fact that ax at y minus delta y by 2 and ax at y plus delta y by 2 are different. The difference exactly is what is coming in here. It seems that we suppress the variation of ax over a range from x minus delta x by 2 to x plus delta x by 2 while keeping, and in fact really insisting on, the fact that ax is different at y is equal to y plus delta y by 2 and y is equal to y minus delta y by 2. So these two demands seem to contradict each other. I say seem to because if I had done this a bit more carefully, I would have been able to show you that the variation of ax over the integral actually gives rise to only higher order effects, things which would vanish in the limit anyway. So this operation that we have done is a legitimate one. And when later on we talk about general curvilinear coordinates, we are actually going to use this argument all over again. However, just to give some peace to those of you who are mathematically minded, let me actually try to do this part of the calculation, at least for the Cartesian coordinates, a bit more carefully, so that you can see for yourselves that even when you do it in a much more rigorous fashion, the final result does work out to be just whatever we had worked out in this particular somewhat sloppy fashion. Note that what we had really done is the following. For the line integral over AB of ax dx, the integral that we had really calculated is this: ax dx prime, where x prime ran from x minus delta x by 2 to x plus delta x by 2. And of the three arguments of ax, the first one here is x prime. Note that this is really a dummy variable of integration which runs from this lower limit to this upper limit. So I have written this as x prime, this as well as a measure of course here, in order to avoid confusion with x, which is one of the coordinates of the point where we are trying to find the curl. The second coordinate is fixed at y minus delta y by 2 all over this integral AB. The third coordinate is fixed at z throughout, and I have just suppressed that for ease of notation. Now what we had done is simply pull this whole thing out by saying that as x prime varies over this interval, the value is essentially the same as that at x, simply because this interval is too small. And after pulling this out of the integral, dx prime of course integrates to delta x. So that was the argument we had used. And of course you would be right in saying that there's a gap in the argument. After all, since we are going to talk about the change in ax when y changes from y minus delta y by 2 here to y plus delta y by 2 for CD, why is it that with the first argument we can completely forget about that variation, just put in the value at x? So let's do it a bit more carefully. For this careful look, it would be better perhaps to look at the sum of the contributions from the two parallel sides AB and CD. After all, these are the two terms which together gave rise to the minus del AX del Y term in the curl. Now these two integrals are simply the following. The first one is simply AB, the same integral that we have seen here. The second term, the one in orange over CD, is very similar with one major difference. That is y, the second argument has been replaced by y plus delta y by 2. And another also major difference, which I should have also mentioned, which is that the limits now go from x plus delta x by 2 to x minus delta x by 2. After all, on CD, the point is moving to the left, that is, towards decreasing values of x. Now, you can easily switch these two limits at the expense of a minus sign and combine the two integrals together. And this gives us a single integral from x minus delta x by 2 to x plus delta x by 2. I've taken a minus sign out overall, so that this term, which has a minus sign because of the switch in the limits, comes in out here first. Ax evaluated at x prime comma y plus delta y by 2 subtracted from this term ax x prime y minus delta y by 2 minus. Now, in order to proceed further, we need to find an expression for this, and a more rigorous expression than simply saying that this is approximately at least equal to del ax del y into delta y, which essentially is what we did the last time around. To do this in a bit more careful fashion, what we need to do is go back to the basic of mathematics, to a result which is very familiar to all mathematics students, at least college students of mathematics, the so-called mean value theorem. This is a very, very well-known theorem, and you will find a proof of this theorem in any elementary calculus textbook. I'm not going to bother giving a proof here, but let me just describe to you what the theorem says. It deals with a function f of x whose graph you can see drawn here. This function f of x has to be continuous in a closed interval containing all the points in between a and b, n points inclusive, and it has to be differentiable in the open interval between a to b. If this happens, then the following holds. There must be a value c somewhere in the interval between a to b, some value of x, at which the derivative of f evaluated as c must be equal to f of b minus f of a divided by b minus a. Now, this may seem like a sort of artificial kind of thing to look at, but the geometrical meaning is very, very simple. F of b minus f of a by b minus a is nothing but the slope of the secant which is joining these 2 points, a comma fa on the left and b comma fb on the right. And f prime at c is nothing but the slope of the tangent at x equal to c. So what this theorem tells us essentially is the following, that for a continuous smooth function, there will be some point inside the interval at which the tangent to the curve will be parallel to the chord that joins the two endpoints. That seems to be rather obvious geometrically. For our problem at hand, what this says is the following. Remember, we want to talk about this difference of ax where x prime is fixed, with the second argument changing from y plus delta y by 2 to y minus delta y by 2. So this is our f of b minus f of a. B minus a here is a change in y, which is simply delta y. This must be the value of the derivative. Here the derivative is with respect to the second argument, del ax del y, the first argument as far as this part is concerned is fixed at x prime. At some point between y minus delta y by 2 and y plus delta y by 2. And that is being expressed here in the form y plus eta delta y, where eta is some number in between minus half and plus half. The mean value theorem guarantees that an eta exists in this interval between minus half to plus half, such that ax at x prime comma y plus delta y by 2 minus ax at x prime comma y minus delta y by 2 is exactly equal, not an approximation, but exactly equal to del ax del y evaluated at a point given by our coordinates x prime and y plus eta delta y times the width of the interval delta y. So, the sum of the two integrals that we are looking at, with delta y taken out of this entire thing, is simply given by minus delta y times an integral of del ax del y evaluated at x prime comma y plus eta delta y over integrated of course over x prime from x minus delta x by 2 to x plus delta x by 2. Note that now you have an integral where the first argument is changing, the second argument y plus eta delta y is fixed. So as far as this is concerned, we can again use a one variable mean value theorem. In fact, the theorem that we can use to simplify this and proceed to the next step is also a mean value theorem. It's called the first mean value theorem for definite integrals, and it can be proven very easily from the mean value theorem that we talked about a while ago. It just says that if a function f of x is continuous in a closed interval a to b, then there exists some point c between a and b such that the integral from a to b of fx dx is simply equal to f of c into the width of the interval b minus a. Now we could use this theorem directly, but I want to take a slightly different route here. I want to give a justification as to why this particular theorem should be true, and it's very easy to actually justify from basic geometrical meaning of what an integral is. So we are back to basics once again. We are just looking at the integral I of a function of a single variable. Note that although the integral there had really three variables as arguments for the integrand, ultimately it was only one variable which was varying, so it's really a one variable integral that we were doing. So if you're talking of some function f of x, and you integrate f of x prime dx prime from x minus delta x by 2 to x plus delta x by 2, this integral I is nothing but the area under this curve. You all know that from basic calculus. Now, if you take the smallest value which f of x takes, f min, and draw a rectangle with that height and width equal to the width of the interval, you're of course going to get an area of a rectangle which is smaller than the area under the curve. So f min delta x is less than equal to our integral I. The equality sign is simply because it might happen that after all your function is flat, in which case this will be exactly equal. Similarly, if you take the maximum value as the height of your rectangle, f max as the height of your rectangle, and delta x as your width, you're definitely going to overestimate the area under the curve, so f max delta x will be greater than or equal to I. Now, if you were to keep on moving the top arm of your rectangle from this value all the way up to this, somewhere in between, as shown here, you will hit a value, a height, at which the area of the rectangle will exactly match the area under the curve. It's too small here, it's too high here. Somewhere in between, it must behave like Goldilocks and the Three Bears case of being just right. And that height is of course what you call f average. Now, what we are claiming here is simply that this height must of course be the value of f of x at some point in between, let's say this point, which is somewhere between x minus delta x by 2 and x plus delta x by 2. So we have decided to call it x plus xi delta x, where xi is between minus half and plus half. So formally what we can say is there exists a xi between minus half and plus half, such that f average is f of x plus xi delta x, and the integral I is simply going to be f of x plus xi delta x times delta x. So going back to our situation, we had this integral to worry about, where your integral was being done over this one variable x prime, ranging from x minus delta x by 2 to x plus delta x by 2. The other argument here stays a constant at y plus eta delta y. So we just treat that as a parameter. So according to the theorem that we have just proven, this integral will have to be delta x times value of this integrand somewhere in between. That is at some x value in between. That is at x plus xi delta x, where xi is between minus half and plus half, you are going to get this as an exact result. So note that here we have not really made any approximation. We have said that the sum of these two line integrals will simply be delta y delta x, the area of this loop, times minus del ax del y, evaluated at some point which is actually inside the loop, some point whose coordinates are given by x plus xi delta x and y plus eta delta y. Now the next part is where it all becomes rather simple. You're going to take the limit as delta x goes to 0 and delta y goes to 0 of this sum divided by the area of the loop, divided by delta x delta y, which means you're going to get del x del y's value and evaluated exactly at the point xy, because in the limit delta x goes to 0, delta y goes to 0, this term and this term go to 0. So the contribution from these two parallel sides to the overall curl is simply going to be minus del x ax del y at x comma y. The contribution from the other two faces very similarly will work out to be del ay del x. I don't really need to repeat the argument here. And so curl of a z component, which is what this would give us, this limit of the circulation divided by the area, is simply given by del x of ay minus del y of ax. And you can of course prove this something similar for the x and the y component, thus justifying the result that curl of A is actually the nabla operator crossed with A. This may be as good a point as any to remind you, the viewer, that our treatment of the divergence in earlier lectures also had this kind of mathematical sloppiness, so to speak, and you can use the arguments that we have just given a while ago to make the calculation much more rigorous. So now we come back to the question that we had raised earlier, the one that we are going to address in the rest of the lecture. Curl of A is del cross A only in Cartesian coordinates. What about other coordinate systems? In particular, what about other orthogonal coordinate systems? Let me remind you that in a general orthogonal coordinate system in 3 dimensions, a given point would be described by 3 numbers, q1, q2, q3. These are the 3 coordinates. Now, if we were to keep q2 and q3 fixed and only change q1, you will get a curve which goes through this particular point. This is the q1 coordinate curve. Very similarly, you can also get a q2 curve, which you get when you change only q2 and not q1 or q3, and a q3 curve in a very similar fashion. what is important is that in a general orthogonal coordinate system, these three curves happen to be perpendicular to each other. So each of these angles that you can see are right angles. Now this is the case for the spherical polar coordinate system where q1, q2, q3 could be r, theta and phi respectively. Also for the cylindrical polar coordinate system and so on. There are many more examples. Now what we need to do is to figure out an expression for curl of a vector field in such an orthogonal coordinate system. And because curl is a vector, what I need to do is figure out all of its three components. What I'm going to do is show you how to figure out one of the components. Say component number 1. The component in this direction. The direction in which the point would have moved if we had changed q1 and q1 alone infinitesimally. Now remember, from the definition of the curl, we know that the curl's component in any given direction is basically the surface density of circulation in a plane perpendicular to it. So what we need to do here is the following. In order to figure out the first component of the curl, what we need to do is to take a loop in the 2-3 plane, a plane in which q1 is held fixed, only q2 and q3 are changed. Of course, the surface which you get when q1 is held fixed would in general be a curved surface, but if you take an infinitesimal loop, then the region bounded by that infinitesimal loop can be taken as a flat region, and E1, our first unit vector, is just normal to that. So this is the point q1, q2, q3 at which we are trying to find the curl, and what we are going to do is to consider going around in a loop A, B, C, D and back to A, and just for simplicity we are going to take the loop which is as easy as possible to describe using q2 and q3 coordinates alone. Throughout this loop, the value of the first coordinate q1 is fixed for each and every point. However, on this arm of the loop, say AB, q1 is fixed, q3 is fixed but not at this value but at q3 minus delta q3 by 2. q2 changes, and that's why I've written it as q2 prime here. q2 changes as you go from here to here. That's for the arm AB. From the arm CD, the same thing happens. q2 changes as you move from C to D. What is important is the value of q3 is fixed here, but it's fixed at q3 plus delta q3 by 2. Similarly, on the arm BC, it is q3 which is changing. So that's why I've noted it with q3 prime. q2 is fixed, but not at the value here, but at a value which is larger, at q2 plus delta q2 by 2. And here, q2 is fixed at q2 minus delta q2 by 2. What we need to do is calculate the circulation in this particular loop gamma, the loop A, B, C, D, A. And that, of course, is a sum of 4 contributions, 4 line integrals over the arm AB, then over the arm BC, then over CD, then DA. Now, the contribution over AB is straightforward. Here, only q2 is changing, and this motion is in the direction of the second basis vector E2. So when you do A dot dl, you are only going to get A2, and that is to be multiplied by the length of this arm, which is h2 times delta q2. Remember, h1, h2, h3 are basically the scale factors. That is, if you change your coordinate by dqi, the point moves through hi dqi. In this case, h2 delta q2. So assuming that this is a small enough region, you can replace this integral by the value of a dot dl there, a dot delta l there, and that's going to be a2 times h2 delta q2. h2 delta q2 because that's the length of delta l, a2 because that's the component of a in the direction of dl here. Well, not only AB, CD will also give you a very similar contribution. Here, over this path is only Q2 which changes, and it changes by H2 delta Q2. So that's what you're going to get. But you have to remember that here on this part of the loop, you're actually moving against the increase of Q2, and that's why it's in the negative E2 direction. So you get a minus sign. And exactly similarly, here you are going to get A3 times H3 delta Q3 with a plus sign. Here, the motion is in the positive 3 direction. Here the motion is in the negative 3 direction. It's in the direction of decreasing Q3. So you get a minus sign for that. So as we have seen several times before, especially when we were calculating divergence in various coordinate systems, you get terms which look like they would cancel, but they don't. These two terms look identical, they have opposite signs, but they are actually evaluated at different places. Q3 plus delta Q3 by 2 for the negative sign part, that is for the larger value of Q3, and for this part over AB, Q3 is smaller, it's just Q3 minus delta Q3 by 2. So these two terms don't really cancel. The difference happens because Q3 has changed, and A2H2 is a term which changes. Note that both A2 and H2 can depend on Q3. So you get del Q3 of A2H2 with a minus sign, simply because larger Q3 value comes with a minus sign here, into delta Q3. That would be the difference of the two contributions times delta Q2, which is always there. Very similarly, this one will not give you 0 because Q2 has changed through delta Q2 between the two terms, and the change is del Q2 of A3H3 times delta Q2. Of course, delta Q3 here comes in for the ride. Once again, let me remind you that there are higher order terms here. There will be terms like delta Q2 square, delta Q3, delta Q2, delta Q3 square, and so on. We are simply going to ignore such higher order terms, because ultimately what we need to do is to find the density of this circulation, divide this circulation by the area delta Q2 delta Q3 into H2 H3, and then take the limit as delta Q2 and delta Q3 both shrink down to 0, and in that limit all these higher order terms with higher powers of delta Q2 or delta Q3 will vanish. So once you divide this whole thing by H2 H3, we get that the first component of curl of A will turn out to be this quantity. Del Q2 of A3 H3 from here minus del Q3 H2 A2. You have to divide this whole thing, remember, by H2 H3 delta Q3 and cancelling out the delta Q3 gives us this final expression for curl of A. In fact, you can make this look a bit better by multiplying and dividing both of these expressions by H1. So you put an H1 up here and divide by H1. The reason why you do that is that now this expression is much easier to write down for the other components as well. This was the first component. For the second component, which will come with an E2 factor, the H1 up here will have to be replaced by H2. Of course, the H3 A3 will be changed to H1 A1 and Q2 to Q3. So 1, 2, 3 will have to be cyclically permuted between the three terms. The first term here is what we have just figured out. Curl of A is one component, and the other two terms is what you get when you just permute the indices 1, 2 and 3 in that order. So this is the full expression for the curl. Now this expression actually makes it possible for us to write this in a much neater fashion, one which is much easier to remember. And that actually follows from this structure. You get H1 E1, then you have del Q2 H3 E3. Here you have H2 E2, del Q3 H1 E1. Here you have similar terms with minus signs. This should remind you of a determinant, and in fact it is. You can easily convince yourselves that this is exactly the same as what you would get when you were to write this down. H1 E1, H2 E2, H3 E3 in the first row. Then you will put the derivatives del Q1, del Q2, del Q3. The second row. Third row, again you will put in H1 A1, H2 A2, H3 A3. But this determinant is not all that you have. You have to divide by H1, H2, H3. So this is the expression for curl of A in a general orthogonal coordinate system. If you know the values for H1, H2, H3, can just plug them in and find out the expression for curl of A in that particular coordinate system. Those of you who know the Levi-Civita symbol would know that this expression can also be written down in this particular form. 1 over h1, h2, h3, then a sum over I, j and k, which is implied in this notation here, of epsilon I, j, k, h, I, e, I, del j, h, k, e, k. If you do not know the epsilon I, j, k notation or the summation convention and manipulations of things like this, don't worry, we will talk about them in a later episode. But for the time being, just think of this as another way of writing down the determinant. Just to see what this tells us about our familiar coordinate systems, the first one would be very simple, just use Cartesian. In Cartesian, of course, h1, h2, h3 are all equal to unity. If you change x by dx, the point moves through 1 times dx and so on. And e1, e2, e3 are nothing but I, j and k. So in Cartesian, this would simply give me I, j, k, del x, del y, del z, ax, ay, az. And that is, of course, the familiar formula for del cross A that we had introduced before. Note that in a general orthogonal coordinate system, the expression for the curl is not really something you can write down neatly in terms of del cross a vector. Although you can perhaps sort of make it look like del cross A, it's pretty similar, but it's not exactly that. But we will continue to call the curl del cross A, no matter which coordinate system we are using. That is just a convenient shorthand to use. Now, to see a more non-trivial example, let's look at spherical polar coordinates. There we know that when you change r through dr, your point moves only through dr. So that's the displacement vector that you have, dr r hat. So here h1, if r is your q1, h1 would simply be 1. If you change theta and theta alone, you move by r d theta in the theta direction. This is your e2, that's theta hat. But r d theta is not the same as d theta. This is dq2, but h2 here is r. And when you change phi and phi alone, you move in a circle of radius r sine theta. And this is your h3, and this, of course, is your dq3, and this is e3. So h1, h2, and h3 for spherical polar coordinates are 1, r, and r sine theta respectively. The product is r square sine theta, which is what goes down in the denominator here. And according to our formula, what you need to do is write down 1 times er, r, that's h2 times e theta, h3, r sine theta times e phi. In the first row of your determinant, del r, del theta, del phi. In the second row, and 1 times ar, r times a theta, r sine theta times a phi in the third row. So this is the formula for curl of A in spherical polar coordinates. I can, of course, expand this determinant out in the standard way of expanding determinants, and this is the expression that I get overall. And sometimes it's perhaps a bit more convenient to take some factors out and rewrite it in this particular form. Frankly, every one of these forms mean exactly the same thing, so it does not really matter which one you prefer. Let me leave the task of figuring out the expression for the curl in cylindrical polar coordinates to you as an exercise. So now we have met all of the 3 members of the Holy Trinity, and we have seen their geometrical meaning as well as some of their basic properties. We have also seen that if you use those operators in pairs, you get new kinds of stuff. Of course, the 2 examples that we have seen so far are important, but the result is not really that exciting. If you apply a curl after a gradient, you get a 0. If you apply a divergence after a curl, you again get 0. But there are many other ways in which you can apply 2 or more of these operations one after the other. In the next lecture, we are going to take a look at some of these properties which leads to rather nice vector identities to deal with. Some other questions would of course also arise before that. These are differential operators, so how do they act on sums of vector fields or scalar fields? Or how do they act upon products of scalar fields with vector fields? Or products of two vector fields, and so on. These and other issues will be tackled in the next lecture. Before that though, we will start our very next lecture with what I have called proof number 2 of Stokes' theorem. The one which is a bit more formal and uses the fact that curl of A can be written down in the form of del cross A. As I have mentioned before, we will need some more advanced bits of mathematics, like Green's theorem in a plane, to tackle this, and we will start by discussing all of these tools that we will need. Bye for now.